Good morning, physics fans. Welcome to the last day of April. That is exactly correct. It's the last day of April. We are turning the calendar after day, and to me, good riddance, April, because it's been a little different this month. So hopefully, the change of the calendar will start making things go in a different direction here. We'll hopefully keep our heads up, and hopefully the weather will change and get some nice warm weather like it's supposed to call for this weekend. So hopefully things will be turning up better. Hopefully everything's going well with you and your household and your family. Once again, if you do have any questions anytime, please feel free to comment me. Please complete the last the problems at the very end that I post for you. Please complete them also, because I use that also with respect to class participation and evaluations into your grades at that point. Today what we're going to talk about specific heat and law of heat exchange. This will be the last of the new material this week. Okay, there'll be nothing else for us this week. Take tomorrow, and if you have to catch up on anything, use tomorrow to catch up on anything. Monday will come in and we'll start going back over we'll start doing some problems at that point in regards to specific heat. This is the last of the new material for this chapter that we will be utilizing. Looking for evaluation sometimes towards the end of next week. And then we have one more chapter left to go, and we'll get through that also. Today we'll talk about specific heat and what happens with specific heat. Let's first take a look at an example of a problem that we've done before with respect to potential energy. If a 0.1 kilogram ball falls 10 meters onto a hard floor and bounces back to 9 meters. Basically, you're talking about like a golf ball. If I would take a golf ball and I would drop it, it's not going to get to a height that I dropped it to, because we don't have perfect ideas here. We don't have a perfect golf ball here. But if I start from here and I drop, here's my height here. So we've lost some distance. Okay, so if we have 10 meters and dropped and only bounces up to 9 meters, how much of the ball's mechanical energy is transformed into the internal energy of the ball and to the floor? And also the sound that we heard. Okay, when you drop this, you hear a sound. That's energy that's being utilized. Well, if we look at the potential energy initially, we are 10 meters high. The mass is 0.1 kilograms, and it's only going to bounce back to 9 meters. So if I take a look at the potential energy at 10 meters, we have mgh, which is 0.1 times 10 times 9.81 meters per second squared. So we have 9.81 meters per second squared. 9.81 meters per second joules is the initial potential energy. If it only jumps up to or bounces up to 0.9 meters, if we find a potential energy at that point, our potential energy is 0.1 times 9 times 9.81. We get 8.83 joules. So if we take a look here, we have lost energy. Well, how does it lose energy? Well, you have the internal energy of the golf ball, you have the sound, you have a little bit of an impact with the floor, so it's not a perfectly elastic collision here. We're going to have some energy loss, and how we calculate that energy loss is by subtracting these two. So we got 0.98 joules of energy that goes into internally what happens with the golf ball, little impact with the floor, the sound, all that energy we're going to be dealing with. Well, when we're talking about heat, that's also what's going to happen. You're going to lose some energy. Okay, we've talked about machines are not perfect. Reason why is because we lose things to friction. We lose energy to friction. That is internal energy. That is thermal energy. Okay, so what we have to take a look at is what is the reaction of the thermal energy at this point? Specific heat. Yesterday we talked about the heat of fusion and the heat of vaporization. Today we're going to talk about specific heat. It's the amount of energy that is added to a mass to raise the temperature of a unit mass 1 degree Celsius, or 1 unit degree. So we're taking metal and we want to raise it 1 degree. Well, the specific heat is the amount of energy that needs to be added to 1 kilogram of this mass to be able to raise it 1 degree Celsius or 1 degree Kelvin, or 1 degree Fahrenheit, does not matter. Okay, so the specific heat is the amount of energy that needs to be added to be able to raise an object 1 degree Celsius or whatever the 1 unit temperature is. That's called our specific heat. The symbol that we use is C with a subscript P. The units are going to be joules per kilogram Kelvin or joules per kilogram degree Celsius. Okay, does not matter, because once again, our degree Kelvin and our degree Celsius are going to be the same increments in regards to what are we going to raise the temperature. We also have kilograms, pounds per degree Fahrenheit if you're in the English units. If we take a look at glass, the specific heat for glass is 6.64 joules per kilogram Kelvin. And once again, this could be Celsius degrees Celsius too. Okay, 664 joules per kilogram Kelvin or Celsius. And once every mass, every type of mass, this is a brass here, okay, this has a specific heat. Water has specific heat. Ice has specific heat. Any type of metals, there's a specific heat, and they're all going to be different. It takes 664 joules of heat to raise 1 kilogram of glass 1 degree Celsius or 1 Kelvin. Again, we don't add the degrees with the Kelvin, it's just understood to be Kelvin. 664 joules of heat to raise 1 kilogram of glass 1 degree Celsius. Well, how much heat would be required to raise 10 kilograms? 10 degrees Celsius. Well, it takes 664 joules to be able to raise 1 kilogram 1 degree Celsius. So if I'm talking about 10 kilograms 1 degree Celsius, how many joules would we have to get 10 kilograms 1 degree Celsius? I have 664 joules. Each kilogram, this is per kilogram, each kilogram requires 664 joules of heat, each one of these kilograms. So to get an entire amount for just 1 degree Celsius, we can multiply these. So we have the 664 times the 10 kilograms. And what this would get us is this would get us 6640 joules of heat to raise 1 degree Celsius or 1 Kelvin. And this is 10 kilograms to raise 10 kilograms 1 degree Celsius or 1 Kelvin. Okay, so we can just multiply our specific heat times our mass. But that only gives us for 1 degree Celsius or 1 Kelvin. Each degree is going to require this amount of heat. Each degree is going to require 6,640 joules of heat to raise that 10 kilogram mass. So how we can deal with this is, well, the first degree is going to cost take this much, the second degree this much, and so on. So we can just multiply this by our 10 degrees Celsius to get us 66400 joules. This is the amount of heat. This is the amount of heat to raise 10 kilograms 10 degrees Celsius. Because each kilogram is going to require 664 joules, we can multiply by the mass to get the number of joules for the 10 kilograms for 1 degree Celsius. But then to get 10 degrees Celsius, each degree is going to require 6,640, so we can multiply by 10 to get us to 66,400 joules of heat. And that would raise 10 kilograms of glass 10 degrees Celsius. The amount of heat Q to raise a mass M delta degrees. How we calculate this is the amount of heat is equal to our mass times our specific heat times what is our temperature raised. Okay, and this is T final minus T initial. We want to think of delta T. T final minus T initial. It's the amount of degrees, the number of degrees we're going to raise our temperature. And this is the amount of heat that we need, MC delta T. But remember, your delta T for Kelvin is also going to be your delta T for Celsius. They are the same degree increments. Okay, it's not going to be like if we're changing to degree Fahrenheit, where 1 degree Celsius or 1 degree Fahrenheit is equal to 1.8 degrees Fahrenheit or Celsius. If we take a look at water, the specific heat for water is 4,180 joules per kilogram Kelvin. The specific heat for ice is only 2060 joules kilograms per Kelvin. So it takes twice the amount of heat to raise the temperature of 1 degree Celsius than it does for ice. Twice the amount of heat. Well, if we compare it to compare it to 1 degree Celsius of ice. So twice the amount of heat to raise the temperature of water 1 degree Celsius compared to 1 degree Celsius of ice. If you have 4,180 joules of heat, will raise water 1 degree Celsius. 1 kilogram of water, 1 degree Celsius. Once again, that's the idea of specific heat. The number of joules it takes 1 kilogram to raise it 1 degree. But if I have the exact same amount to ice, this would raise the ice 2 degrees Celsius. Now, ice is not always going to be just at 0 degrees Celsius. You can get ice at a lower temperature. It does not have to just, if I have ice, it must be 0 degrees Celsius. No, it may be -2, -4, -5 degrees Celsius, depends on the environment. So it does not have to be exactly at 0 degrees Celsius. For it to melt, you have to take it to 0 degrees Celsius, then it takes it to 0 degree Celsius water at that point. So if you have this 4180 joules, it's going to raise 1 kilogram of water 1 degree Celsius, but it's going to raise ice, 1 kilogram of ice, 2 degrees Celsius. On the back, I just have some general ideas about your car. Your car has what is called antifreeze in it or a coolant in it. Okay, it's either an antifreeze or it's a coolant. It's a dual purpose thing. Why? Because we have a wide range of things. Well, this is ethylene glycol. But sometimes people will just use water and put water in the radiators. What that radiator or that ethylene glycol does is it cools your engine. It cools your engine down. It allows heat to be taken away from your engine because your engine has a lot of friction. Okay, so it has a lot of friction, it builds up a lot of heat, and it needs to be cooled somehow. Well, that is the coolant that you have here. But it also acts as an antifreeze, so it does not freeze up also. The fluids in there don't freeze up. If we take a look, here's our freezing point, and this is all in Fahrenheit. Okay, freezing point of water is 32, ethylene glycol 8.6, but if you mix them together, which I found is always interesting, it goes down, the freezing point is -36 degrees Fahrenheit, which is, when I think about that, it's like you got two things that you mix together. Okay, the solution has a lower freezing point than both of these put together. But if you take a look at the boiling point, you have 212 degrees Fahrenheit, 387 degrees Fahrenheit, and you have 225 degrees Fahrenheit for it to start to vaporize, the boiling point. You start vaporizing, then you start overheating. Okay, so you have to worry about these types of things. And then you have some specific heats down here. Heat of vaporization, but these are all in English units. Law of heat exchange. The law of heat exchange. In an isolated system, heat lost by a hot object equals the heat gained by a cooler object. Now we're talking about an isolated system. In an isolated system, the warmer body will lose heat. The cooler body will gain heat until you get to a thermal equilibrium. Goes back to, even though this is not an isolated system, when I drop the ice cubes in this water, the water was warmer, the ice was colder. Okay, what you had is you had some interchange of heat, some heat exchange here. The cooler ice cubes lost heat or gained heat from the warmer water. And we'll do an example of this on Monday. The law of heat exchange. An isolated system, heat lost by an object is gained by a second or a cold object. When you have an endothermic process, this is the absorption of heat. Okay, so if you think about the ice cubes absorb the heat from the water. That's called an endothermic process. Then you have an exothermic process, which is the loss of heat or the release of the heat. So the water in the ice cubes lost heat to the ice cubes, so that's an exothermic process. And the last thing with the law of heat exchange. Once again, this must be an isolated system. And it does not matter how many masses you have here. Okay? But I take the MC delta T of one object added to the MC delta T of a second object and the MC delta T of a third object. And if I take all these up, I should add up to 0. Now, you can have as many objects in here as possible. If you want to add in a fourth object, that is fine. But what you'll see is, you'll see some of these are going to be positive and some of these are going to be negative. Why? Because my delta T is going to be, some will be positive, some will be negative. The water lost heat. Okay? So my delta T is T final minus T initial. It's going to be 20 degrees, or I'm sorry, 16 degrees minus 20 degrees. So it'd be a -4. My delta T would be a -4 here. So some of these quantities will be negative because they've lost heat. Okay? If they have lost heat, once again, you have an exothermic process. The water was losing heat. So it has a negative Q here. If it has a negative Q here, then it's going to be exothermic because it's releasing the heat. The ice gained heat, so my ice went from 0 degrees Celsius up to 10 degrees Celsius. So that was T final minus T initial, which is a positive 10. So that gained heat, this would be a positive quantity. Once again, MC delta T, if I add up all the MC delta T's, I should add up to a value 0. That is the law of heat exchange. But once again, I need to make sure I'm in an isolated system and I'm not taking other heat from outside and adding more heat from the outside at that point. This water here in this beaker is not an isolated system. Why? Because you have the 70-degree air from the room that's also affecting the heat of this water at this point. We'll talk about a calorimeter on Monday. I'll bring a calorimeter in, and we'll talk about what a calorimeter is. The ideas of insulated cups, the foam insulated cups with a lid on it, is close to what an isolated system would be. You would still lose some heat or gain some heat from the interior or exterior because the environment, because you have a little, wherever you put your straw or the lid for your coffee cup. Okay, you don't have, you lose some heat or gain some heat. Yetis are insulated things. So you wouldn't get very much from the exterior into here to melt or to cool down the water at that point. So Yetis are fairly good with respect to an isolated system because you can keep ice cubes in here pretty much all day long. Okay, you will keep on adding water, and that's how you lose the ice cubes, is you keep on adding water into this, which is at some 30 degrees or 40 degrees, and then it will melt the ice at that point. But Yetis are pretty good isolated systems. Once again, complete the problems or the things I put at the very end here. Utilize tomorrow as a makeup day. If you haven't kept up with the material, utilize tomorrow to be able to do that. Monday we'll come in and we'll go over any type of, or we'll start going through some problems. We'll take some ice cubes. We'll get the ice cubes out here. We'll melt some ice cubes. We'll get some metal here that's hot. We'll get some metal that's hot. We'll put it into cooler water. Okay, and we'll talk about what happens thermally in an ideal situation with respect to cooling of elements. So that's what we'll be talking about on Monday. Other than that, I have nothing else for you this weekend. Have a good weekend. Once again, utilize tomorrow to make up any work. If you've been keeping up with the work, you have nothing to do tomorrow. So you can do what you want to do at that point. So I have nothing else for you though. I miss you guys. I wish you were in class. But this is our reality. Once again, we'll be okay. We'll be okay. Like I said, we're turning the page to May. We're flipping the calendar up to May. We'll be fine on this, all right? You folks have a great weekend. Adios. We'll see ya.